Hello everyone, I am excited to provide a demonstration of our inductor synthesis tool, ModInd. Unlike most tools out there, ModInd has unique capabilities to enhance our RFIC designer's output. It aids in the design of inductors and transformers that are needed for matching networks which are essential to any RFICs. To compare against some very good tools out there, ModInd is able to produce most basic structures like single-ended inductors, fully symmetric differential inductors, balun, and asymmetric transformers. In addition, using high-level scripting, ModInd is able to take very simple and practical inputs, and calculate and generate the required inductance needed for the given application. For example, ModInd is capable of taking input and output impedances as input and produce the required matching network components which already take into account the parasitic self-loading effects. Let's dive deeper into what ModInd can do for you. I will briefly go through ModInd's capabilities and describe the approach that is being used to improve the designer's efficiency. We will then watch a live demo of how to use the tool with Keysight ADS. We will talk about the tool's accuracy in the end. Designed by an RFIC designer for RFIC designers, ModInd always operates from the designer's perspective. The approach is PDK agnostic and eases portability. ModInd's goal is to reduce the time RFIC designers spend on repetitive tasks, such as iterations needed to take into account the inductor's self-parasitics. It also provides users a simple way to design amplifiers, baluns, and other components needed to design RF phased arrays and clocking circuitry. ModInd's I/O is designed for higher-level inputs such as circuit parameters like device S parameters, topology, etc. It also generates intelligent fills, patterned ground shields, ground rings, and lets the user customize input and output stubs to better fit top-level layout. It also provides ways to scale the inductor, should the need arise later. The inductor dimensions are always kept on a higher-level grid to ease top-level integration. Let's quickly take a look at the time savings over conventional RF design cycle. Most RF design cycle begins with translation of specifications to active device size. Once active device size is already determined, the designer needs to create the passive networks that is needed to provide matching. The passives will then need to be laid out, EM simulated and resized to finally meet specifications. From this stage and once full layout has been created, the designer will need a few more iterations to take into account any routings. ModInd provides scalable inductors with the backing of EM simulation, thus drastically reducing design time by letting designers skip multiple iterations needed to create passive networks. On average, one can expect over 6x faster design closure. Now let's see ModInd in action. We will use Keysight ADS and Momentum as the base software for this demonstration. Here I have Keysight ADS open and workspace loaded. Upon installation, you will be able to see an additional menu item, ModInd. Let's click on Start ModInd, which will open a GUI for a ModAnalog's inductor synthesis tool. Once you log in, there are options to select the PDK profile or the type of inductor that is to be designed. Let's select a single-ended inductor. Single-ended inductor API is a lower-level API that lets the user pick the number of turns, inductance, operating frequency, and other physical parameters, for example, if a patterned ground shield is desired, whether to do intelligent metal fill and draw ground rings. You also have an option to select how far the input ports need to be extended. The port extension is an important input as it minimizes the number of iterations that would have been needed to include any metallization that is generally needed for the connection to devices. Finally, there is an option to select an aspect ratio and scaling factor. Once we submit the desired inputs, the API returns a first-cut design of the inductor along with an expected model that can be used for simulations. After this step, we go back to ADS and click on Optimize the Inductor menu option. This runs momentum simulations in the background and optimizes the inductor to the precise inductance value within the preset accuracy limits. Let's look at the inductance that was created. As we can see, the layout has been loaded into the ADS. Also, do note that the ground ring, PGS, and metal fills all come as hierarchical cells, thus giving the user full control of the EM simulation time. Now let's look at the accuracy of the inductor generated with a demo bench. Here we can see that the achieved inductance is precisely 303.5 picohenry with Q greater than 20. The Q achieved in this process is also quite high as the tool has an inbuilt optimization of area and quality factor. Now let's go back to our GUI, press on Home, and select an advanced functionality of Generic Matching Network. This is one of the most useful aspects of RFIC design, and the use cases are shown in the picture on the right. The same functionality can be used for input matching, output matching, or interstage matching. The scripts here are designed to provide high-Q narrow-band matching while ensuring manufacturability. Let's take a quick look at the GUI here. We need source impedance, load admittance, and the frequency at which the matching is to be done. Other options are similar to what we needed for a single-ended inductor design. I have entered some default values. Let's submit these inputs and check what we get. The tool provides the matching network that is needed to achieve the required matching. Besides, it takes into account an approximate parasitics of the inductor. After this step, we go back to ADS and click on Optimize the Inductor menu option. This runs momentum simulations in the background and optimizes the inductor to the precise inductance value within the preset accuracy limits. Now let's check the matching performance based on actual inductance that has been created. I have created a test bench for demonstration purposes. As we can see, a very good matching has been achieved. Let's take a quick look at another benefit that allows the user to design a low-noise input matching. Here, the user needs to provide the device transconductance, gate source capacitance, and the operating frequency. Let's submit the inputs that have been pre-filled. The tool generates an asymmetric transformer that achieves the required matching. Note that to optimize the noise, the minimum input return loss is set to -8 dB. Post-optimization, here is the generated transformer. Let us plug this transformer back into a test bench and look at the results obtained for input matching. As we can see, a good input matching is obtained while maintaining a high gain. On a final note, we also provide users with the capability to generate their balance, symmetric inductors, and low-area stacked inductors for use as chokes. I hope you enjoyed the video. Please reach out to me at ssah@modanalog.com to start your trial and save your company's valuable RFIC design resources. Happy designing! Bye.